So good day everyone. Our topic for today is all about prime numbers, greatest common divisor or GCD, and fundamental of arithmetic. So now let's discuss about prime numbers. So what are prime numbers? So based on the theorem, it is a positive integer p greater than 1 is called prime if the number positive factors of p are 1 and p. A positive integer that is greater than 1 and is not prime is called a composite. So, prime numbers must have only two possible unique factors. Both factors cannot be the same. So take note of that. It cannot be the same. Therefore, the example for this is 1 because the factors for 1 is 1 in itself, so they are the same. So 1 is not a prime number. Next, in a prime number, one factor must be 1. Always bear that in mind that the first factor of a number is only 1 and the other factor must be a whole number but not 0 and 1. So there are a common misconception about prime numbers that all odd numbers are always prime numbers, but that's not true. Yes, of course, um, not all odd numbers are prime because as what I've said, 1 is not a prime number and 1 is an odd number. Okay, so how to determine if a number is prime? So to determine if a number is prime, place it in the product position. So when you're going to use the product position, you're gonna have this diagram. Okay. In the first factor, or in the first box, you have same number as the product but not 0 or 1. And the other factor is 1. It is constant that the other factor must be 1 and the product would result to the same number as the product but not 0 or 1. So now let's proceed for the examples for you to have a clearer understanding. So first example is 5 a prime number? Is 5 a prime number? So now let's think of a number or the numbers that could be possibly factors of 5. But there's no other factors of 5. So when you put that in a product position, 5 times 1 times 1 is this 5. It is 5. And it would result to 5. Sorry, equals 5. Obviously, 5 is an example of prime number. So let's move on for the next example. Is 21 a prime number? Okay, let's use the product position. You have 21 for the factors of 21. You have 21 times 1 and of course 7 and 3. Therefore, there is other factor except for 21 and 1. Therefore, this is not a prime number. Okay, that's clear? So now let's move for the next example. Third example is 121 a prime number. Let's think for the factors of 121. Of course, 121 is the factor of 121 and 1. And the other factor would be 11 and 11. So, therefore, there are another factor of 121 except for that in the principle that it must be the number and 1. Therefore, this is not a prime number. Okay, let's move on. For the number 4, is 1021 a prime number? Let's think of a number or the factors of 1021. But obviously, the factor for this is 1021 and 1, right? Okay, and this would result to 1021. But when we think for possible factors, there's no other. Therefore, we can conclude that 1021 is a prime number. This is a prime number. So now let's move on for the fifth example. The fifth example is 99,999, a prime or composite number. Okay, let's think or brainstorm about the possible factors of 99,999. So we have, of course, 99,999 by 1. The other must be 3 multiplied, 33,000 and 33,333 multiplied by 3. You've also, if you simply look in this number, the 99,999, obviously 11,111 and 9. So in this case, as you can see, there's a lot of factors for this number, right? So therefore, we can say that 99,999 is not a prime number. Is that clear? So, okay, 99,999 is not a prime number. Therefore, it is a composite number. It is composite number. And for you to have a more learnings or more knowledge in regards with prime numbers, so I'm going to give you some trivia of it. Okay? Prime numbers are also called non-composite numbers. So composite numbers are numbers with many possible factors. Following this principle, all even numbers aside from 2 are composite numbers because 2 is the smallest prime number. Okay, let's discuss about that later. Next is 0 and 1 are not considered prime numbers. Why? It is because when we multiply 0 to any number, the answer would be 0. Thus, it is not a prime or it is not included in the principle of a prime number. While in the case of 1 is different. Yes, I've mentioned earlier that 1 is not a prime number because the factors for this is 1 in itself, therefore they are the same. So 1 is not a prime number. Let's proceed to, okay, so we have 2 is the smallest prime number. Because of the principles of prime numbers, it says that it must be only one factors, the number and 1. So when we think of a numbers, it could be factors for 2 is we have only 2 and 1. Therefore, even if it is even number, then it is a prime number. Because it is not stated there in the principles that even numbers, yes, I've mentioned that it is a misconception. Therefore, 2 is the smallest prime number. Next, the largest prime number found so far has 24,862,048 digits. So it was discovered by Patrick LaRoche on December 7, 2018. The number is known as NH2589933. Um, this is the largest prime number currently. So take note for that. It has 24. Okay, it has 24,862,048. No prime numbers greater than 5 end in 5. We're gonna prove this one. So 5, we all know that the factor of factors of 5 is only 5, and 5 and 1, right? So 5 and 1 equal to 5. So this is a prime number, right? So it says that there's no other prime numbers that ends with 5. So example, we have 15. Is 15 a prime number? This is not a prime number, basically, because 15 will be factors for 15 and 1. And also 5 and 3. It is very clear that this number has another factor except for 15 and 1. Therefore, it is not a prime number. So let's try for 25, because 25 ends with 5. 25. So the factors for 25 is we have 25 multiplied by 1 and also 5 multiplied to 5. So therefore, there's also a factors except for 25 and 1 and 5. 25 is not a prime number. And also same with the other numbers that end with 25. With 5, I mean. So let's proceed. Okay, 73,939. Okay, the next is 73,939,133 is a unique prime number. So this number is very unique because it has peculiar property. So when we say peculiar property, it comes from the Latin peculiaris, means privately owned or special. So look at this number, which is this one. So it will keep on removing a digit from the right side. Each remaining numbers is also prime. So when you remove the digit, one digit in the right, so we remove this one, it would be the remaining. So the remaining is this. It says that it is also prime, and it is correct. It is also prime. And keep on removing another one, another digit. We have this one we're going to remove, and the remaining is also prime. So try it in your own, and you're going to find that this is true. So take note of this. Next, prime numbers that are two spaces are called twin primes. They are called twin primes. So example for this is we have 5, because this is prime, and also 7. This is also prime. So this is what we call the twin primes. Twin primes because there are two spaces in between of them. You're gonna add 2. We're gonna add 2 for 5, then you get 7. So this we called twin primes. Next is also the same with other numbers. Prime numbers that have 2 spaces is automatically called as twin primes. The other is, I think this is the last trivia. So the product of 2 prime numbers is called semi-prime. So this is, example for this is, I'm going to use again the 7 and 5. So we have when we multiply 5 into 7, we get 35. In the product, it is called the semi-primes. So 5 multiplied by 7 equals 35. Therefore, the semi-prime here is 35. And also, because there's a lot of prime numbers, there's also a lot of semi-prime. Just take note for that. Okay, let's proceed for the prime number trick. I'm going to give you this trick I've found in the internet. Okay, here's the steps for this trick. Pick any number greater than 3. Okay, the first step is to pick any number or choose any number, prime number that is greater than 3. And then square it. Then add 14 for the answer, and next is to divide by 4 or 12. And the remainder will always be 3. So we'll have an example. Let's try 5. For it is a prime number that is greater than 5. 3 and 5 is greater than 3. Therefore, we can use this number, 5. Then the second step is to square it. When we square 5, we get 25. And then the next step is to add 14. So 25 plus 14 is equal to 39. And the next step is to divide this into 4 or 12. So let's try. Let's check if the remainder is really 3. So we divided 39 divided by 4 is, we have 9. Multiplied 9 to 4. The answer is 36. When we subtract this one, 3. So this is the remainder. So it is correct that 3 is the remainder. So what if we're going to use 12? So again, we will use 39 and divide it into 12. We have 3 here. When we multiply 3 by 12, we have 36. And subtract it, we have 3. Also, this is accurate. 3 is the remainder. Now let's have another example to prove that if really this number, this trick is right. We're gonna use the 2-digit and okay, 17. Next is to square it. 17 squared, the answer would be 289. The next step is to add 14. So 289 plus 14 is equal to 303. Then 303 will be divided into 4. 303. So 303 divided by 4, we have 7, and then 28, 2, 3, 5, 5, then 20. Still, the remainder is 3. So we're going to try for 12. 303 divided into 12. It is 2. 12 and 24. And we have here 6. And we subtract 32, 24, 6, and then 3, we have 63. And 5 to 63. Therefore, this trick is applicable also for 17. So just always remember that if you're gonna choose any number, be sure that it is prime. Okay, it must be greater than 3. And I think that concludes about prime numbers.
Greatest common divisor or GCD. So we've here the theorem says that let a and b be integers not both 0. The largest integer d is such that d divides a and b is called the greatest common divisor of a and b. We have here the steps in finding the GCD. To find divisors of a number, make a list starting with the lowest possible factor, which is 1. We have here the example 20 and 40. The factors of 20 are 1 times 20, 2 times 10, 4 times 5. The factors of 40 are 1 times 40, 2 times 20, 4 times 10, and 5 times 8. When two numbers have the same divisor, it is called a common divisor. For example, 12 and 6. In order to find the GCD of 12 and 6, we find first the factors or the divisors of 12 and 6. The factors of 12 is 1 times 12, 2 times 6, and 3 times 4. The factors of 6 are 1 times 6, 2 times 3, and 3 times 2. The common divisors of 12 and 6 are 1, 2, and 3. In order to get the GCD of it, we should multiply their common divisors. So 1 times 2 times 3 is equal to 6. Therefore, the GCD of 12 and 6 is 6. The largest number divides evenly into a given set of numbers. It is useful to know this for reducing fractions. There are two ways to find the GCD. Method number 1. List all the divisors of both numbers, then find the greatest common divisor. So the divisors of 12 are 1 times 12, 2 times 6, and 3 times 4. While the divisors of 30 are 1 times 30, 2 times 15, 3 times 10, and 5 times 6. The common divisors of 12 and 30 are 1, 2, 3, and 6. So the GCD is 6. Method number 1 is here, but you have to list all the divisors for both numbers. That's why there's method number 2. Method number 2. Find the prime factorization of the two numbers, then multiply their common factors. The factors of 12 are 2 times 6 and 2 times 3. And the factors of 30 are 2 times 15 and 3 times 5. The factors of 12 are 2, 2, and 3. And for the 30, the factors are 2, 3, and 5. The divisors of two numbers which is common is 2 and 3. In order to find the GCD, we need to multiply their common factors. 2 times 3 is equal to 6. Therefore, the GCD of 12 and 30 is 6. In relation with the last reporter, we can use GCD in determining if the modular arithmetic has an integral solution or not. We have here the example 36x is equal to 432 mod 42. We need to find the GCD of a and n. Here is our a, b, and n. So the factors of 36 are 2, 3, 4, 6, 9, and 12, while the factors of 42 are 2, 3, 6, and 7. Therefore, the GCD of 36 and 42 is 6. In determining if the modular arithmetic is an integral solution or not, we need to come up with a quotient, or the quotient is a whole number. So 432 divided by 6 is equal to 72. Therefore, this modular arithmetic has an integral solution. Example number 2. 56 is equal to 28 mod 7. Like in the last example, we need to find the GCD of A and N. A, B, and N. So the factors of 56 are 1, 2, 4, 7, and 8. While the factors of 7 are 1 and 7. Therefore, the GCD of 56 and 7 is 7. 28 divided by 7 is equal to 4. Therefore, this example has an integral solution. Example number 3. 32x is equal to 52 mod 44. Here is our A, B, and N. The factors of 32 are 2, 4, 8, and 16, while the factors of 44 are 2, 4, 11, and 22. So the GCD of 32 and the GCD of 32 and 44 is 4. 52 divided by 4 is equal to 13. Therefore, this example has an integral solution. Last example, 21x is equal to 49 mod 7. So here is our A, b, and n. The factors of 21 are 1, 3, and 7, while the factors of 7 are 1 and 7. Therefore, the GCD of 21 and 7 is 7. 49 divided by 7 is equal to 7. Therefore, this example has an integral solution.